Yeah, am I audible, guys? So please type in the chat box. Good evening, but yeah, please type in the chat box. Am I audible? Good evening, all. Mudit. Yeah, good to see all of you back after some days. Satish, Sukumar. So please type in the chat box. Am I audible? Is my audio and video clear? Clear. Great. So welcome back finally. Actually, जब मैंने fluid mechanics लिया था उस टाइम पे मैंने सोचा कि that's the last subject I'm going to take in fast track. लेकिन last moment पे Vinod sir, I have to, me and Vinod sir has to exchange the subjects actually. Fine. So we'll start applications of thermodynamics. Both clear. Okay, great. So first of all, before starting applied thermodynamics, I want to ask you a few things. How many of you felt fluid mechanics was very fast? Genuinely, please type in the chat box because I want to, do certain changes. How many of you felt fluid mechanics as very fast? So please keep rate of speed slow. In FM, you are too fast. Yes, exactly. That's what I am asking. Yes. Okay. So this time you have a happy news actually. Thermodynamics don't involve much maths as that of fluid mechanics because clearly we deal only classical thermodynamics. Of course, even in fluid mechanics we were dealing only classical mechanics, but majority of you who felt like there was a lot of maths, there was a lot of vectors, integrations, differentiation of functions, all these things I was using in fluid mechanics. So some of you, but actually it's needed to gate level. Okay, so that's why some of you might have felt fluid mechanics as slightly complicated, but actually things are very clear. If you just play the video a bit slowly or something, you can understand the things. Okay, same pace as that of FM. Okay, great. In thermodynamics and of course in applications of thermodynamics, you don't need much of maths actually. Okay, only basic things is few integrations when you're calculating work interactions, and of course since basic thermodynamics is already done, normally in thermodynamic relations we'll use small bit of differentiation as well. But anyway, we need not do any of these things because in applied thermodynamics only multiplications and divisions is what you have to do. Okay, so mathematically no issues. But before starting this course, I want to tell you a few things. Like this is the last subject of 4 p.m. to 6 p.m. batch, I guess, correct? Like we were taking 2 sessions per day. One is from morning 8 to 10 and one is from 4 to 6. So definitely like this is the last subject. We got enough time, like almost some 13 days in between 2-3 holidays if they go. Still we had some good time. I'll teach complete, of course, this applied thermodynamics. Meanwhile, I'll also teach you compressible flows because when I taught you fluids, there was no enough time. So I didn't teach you compressible flows actually. So here I'll teach you compressible flows as well. Okay. And also, if any of you need any math, like for example, when I'm teaching fluid mechanics, some of you may find difficulties, or if you need any concept in mathematics a bit, then definitely ask me. I'll try to take some time, maybe some 5 to 10 minutes of every, or 10 to 15 minutes of every class, and I'll try to discuss the topics. Okay, and as I tell you always in my class, you need not hesitate to ask any doubts. अगर आपको किसी भी doubt है तो okay, even a small point, you can always ask me here. Clear? So previous year no question from this subject. I'll tell you one more important data. In 2022 also no question. Okay, so that's why in 2024 definitely we are expecting few questions from this. I'm expecting around 3 to 4 marks of applied thermodynamics will be there actually. Okay, because for past 2 years there's no question actually from this. Of course from compressible flows there was question, but it's always an ambiguity between fluid mechanics teacher and ATD teacher to decide whom to teach compressible flows actually. Okay, but anyway I'm taking, so no issues because both subjects are being done by me. Now I cannot escape. Okay, so anyway, today since you guys have started the fast track with basic thermodynamics, काफी time हुआ था, 2 महीने हुआ already, so I thought it will be slightly good if I just review all the basic thermodynamics. So इस लेक्चर में हम पूरा basic thermodynamics को फटाफट से रिविजन करेंगे, and उसके बाद कल से मैं IC engines सब चीज. Okay, normally I'll give you the flow of the course also, like what are the sequence of chapters which I'm going to deal. So all these things will go on. Okay, so I have completed the lectures of ATD but not revised a single page. Can you guide me with this approach with the fast track? Just follow the fast track, complete revision happens. Okay, and sir previous year, okay, I have answered. XC maths practice, wait till January. Okay, because अभी schedule थोड़ा सा आसान नहीं है. So please read my comment. I have read. MSQ theory भी complete करना है. MSQ theory भी complete करना sir. MSQ, yeah, generally MSQs come in gate examination. Last year also I think 2-3 MSQs आया था. I think 4 MSQs actually, 4 आया था. So but I'm telling you one thing, if you learn concepts in a clear cut way, it doesn't matter it's an NAT or MCQ or MSQ, you will be always able to answer the questions correctly. Okay, so just focus on the subject. Clear? So anyway, in this lecture today, I'm going to talk about, of course, the complete basic thermodynamics. So we'll have a quick discussion on basic properties, first law of thermodynamics, second law of thermodynamics. I'll also talk about 𝐂𝐻𝐺 relations, and in between at the end I'll also talk about pure substances. Okay, so this is the way how we are going to progress today. And before straight away going for the topics, if I just want to give you some insight how I'm going to cover the things, first we'll have a view of thermodynamics, a view of basic thermodynamics. Then after I'll start A standard cycles. Actually only A standard cycles is there in the syllabus, but I'll also slightly talk about powers, efficiencies, loading on IC engines, a certain small amount of test, all these things. Okay, because if some of you are writing ESE or ISR exam is also about to come. Okay, so if some of you are doing that, it would be helpful for you. Then so A standard cycles, basically in a nutshell, I'll teach IC engines around. We'll talk about mean effective power, indicated powers, all these things. Then we'll then move for vapor power cycles, Then we'll basically talk about Rankine. We'll see conversion of Carnot to Rankine cycle. What are the complications in Carnot cycle? Why we are coming for Rankine cycle? And then we'll also talk about the both important concepts of reheat and also regeneration concept also we'll use a bit. Okay, so we'll try to identify different things. So XC part will also be covered. Yes, actually I want to make one comment here. If you take XC syllabus of ATD, XC syllabus of ATD is less than mechanical syllabus of ATD. Okay, and right now I'm going to take the subject at the mechanical level so that your complete XC will also get covered for ATD. Okay, so just focus. Then once you're done with the vapor power cycles, we'll revisit gas power cycles again. Normally here also the cycles, A standard cycles, whatever we did, they are gas power cycles. So we'll again talk about gas power cycles. Then we'll talk about Breton. And basically using the concepts of regeneration and reheating and all, we'll also talk about Ericsson and Ericsson cycle generally, because regenerations and all, and Stirling also we'll see if time permits. Okay, I'll see, no issue, because sometimes questions comes. So Stirling, and we'll see these cycles, and in Breton cycle we'll again talk about the concepts of reheat and regeneration. Okay, regeneration is very powerful in case of gas power cycles. Okay, we'll see why and all as we progress through the course. Then we'll talk about we'll also talk about so once gas power cycles are done, then where shall we go? Refrigeration and air conditioning will go. Refrigeration and air conditioning. In air conditioning, many of the students feel discomfort because sometimes people ask you to mug up the formulas. Like for example, if you have this formula, people write 0.622 PV by total minus P vapor. Majority of students, they don't know how this 0.622, all these things are coming. We'll see everything in detail because we had some time this time. Okay, so refrigeration and air conditioning also we'll see. Then after this, we'll also talk about compressible flows. We'll talk about in compressible flows, we generally talk about all the basic stuff, then the relations, and also we'll see normal shocks. Oblique is not in syllabus, I guess. Even we don't know, even normal shocks is also there, but anyway, for safe side we will study. So normal shocks we'll see, and also converging diverging nozzles, CD nozzles, because in case of rockets and all, this is very important. And there's one important concept of back pressure which generally people can ask if they want. Okay, and before this, whatever is basics of compressible flow, like area versus Mach number relations, area versus velocity, if flow is subsonic, why nozzle acts as accelerator and why diffuser acts as diffuser. Basically we'll diverging cross section acts as diffuser. We'll see all these things. Okay, so we will spend all this basically this is the nutshell that I'm going to cover in this particular fast track course. Okay, so 1 2 3 4 5 6 topics roughly. And anyway, this is only for one lecture, review of basic thermodynamics. Okay, so these are the things that I'm going to cover for you in this particular course. Do you expect any other things for me to cover in this case? Sir, PVTS HS graphs वाले भी करना बहुत confusing होता है. Definitely मैं करता हूँ. Okay, so जब मैंने refrigeration पढ़ाता हूँ उस टाइम पे सारे pH, okay, pressure versus enthalpy graphs, and इस सारे चीजों में PV and TS दोनों बनाता हूँ. ठीक है? Clear? Is this content, this is what I'm planning to cover in this course. Do you need any other things, or do you expect any other things that I should cover in this course? And generally for mechanical, I think this is good enough. And in XC you don't have regeneration parts here, you have only heating. And compressible flows, I think it is there or not there in XC, we have to look over a while. Okay, now let's see. So let us straight away start with basic properties. Okay, so I'm not going to again go for all these things. Thermodynamics is basically like combination of two words, therm and heat, dynamics. Okay, so this word was first introduced in 1849 roughly by Kelvin, Lord Kelvin. He coined this word in one of his research papers, and then after first textbook was written in 1859 roughly on this thermodynamics. Okay, and Rankine, actually William Rankine is one who have done it. Anyway, this is a bit of basic stuff, and therm is basically heat and dynamics is basically power, and this complete science is talking about this. Okay, so conversion of heat to power and power to heat. Initially the idea was only conversion of heat to power, normally the steam engine, all these things were there, but later when with the development of refrigerators, air conditioning and a lot of other things, we know, like even your iron box. Okay, so conversion of power to heat. So basically it talks about the equilibrium between these two things. Okay, heat and power. Now if you see, we'll talk about some basic things which is like system. So what is a system actually? A quantity of matter or region in space, because sometimes region in space that is under study, actually. Okay, so basically sometimes what we do, we'll actually take some small amount of matter which is of our interest, like for example if I take a for example oxygen, okay, in some small container, then if I'm heating it, what happens to this particular what happens to this particular gas? So studying that is actually quantity of matter, because I have because I took some small amount of mass of gas and trying to analyze it. But let's suppose if I'm investigating what's happening inside a tank. Okay, let's suppose when I was working with HPCL, there were a lot of tanks in which I was working. So let's say there's a tank. Okay, so to the substance which is inside the tank, what is happening? So in that case, the volume of the tank is of our interest, and we will look at what's happening inside the tank. Okay, so that's why to study some important properties of the things, sometimes some finite amount of mass is taken, or sometimes some amount of region is taken. Normally this is called control mass and this is called control volume. Regarding this we have seen a bit in fluid mechanics also, regarding the control volume. The nightmare, RTT, remembered? I was talking about the Reynolds transport theorem when we were talking about the property changes of control volumes. You remember that equation with which I have scared so many of you, writing integral of cross product of something into something, all these things. Do you all remember that in fluid mechanics we were talking about this control volumes? Anyway, now also we will talk. Now see one thing clearly, properties. So any measurable characteristic of a system, any measurable characteristic of a system which can be given a number at any instant. Means let's say for example if the process is, for example if there is a gas which is delete okay. So see here, a number at any given instant. So let's say for example if I have the same amount of gas, now let's say this gas is going under some process. Okay, so from state 1 to state 2. So at any point during this process, at any instant of time, I should be able to define the properties of the gas. Like for example, let's say for example if expansion is happening for 4 seconds, okay, then at 2.6 seconds if you ask me what is the pressure, what is the temperature, I should be able to tell. Okay, so that's why you should be able to give its property at any instant, and this any instant independent of past history, actually independent of past history. Means at 2.6 seconds when I'm talking about pressure, it doesn't matter for me what's the pressure, 2.5 or 2.4 or maybe 2.1 seconds. Okay, so at that particular instant I should be able to assign some number to this particular gas and I should talk about the values. Okay, so now clearly these properties are extensive, intensive. I think Shivam sir might have fantastically taken you through all these things. Intensive. Now this doesn't depend on extent or size, extent or basically size. But whereas these guys, they depend on size, depend on extent, in general mass, you know. Now you can see a big list. By this time you will be very much happy to write all these independents: pressure, temperature, density, kinematic viscosity, dynamic viscosity, thermal conductivity. Okay, so all these things. Then coming to this extensive, you can say mass, volume, entropy. Okay, so all these things again. Okay, so what else we can say? Mass, volume, entropy. Heat and work are not properties, actually they are functions, path functions. So fine, we will see end of my thinking capacity. Maybe after this we'll find some more, we'll write that. Okay, so please read my comment. Mohit sir, approximately how many lectures and weightage of applied? Around 3 to 4 marks generally. Okay, and how many hours? I think 12 into 2, 24 hours I'm going to take. Okay, roughly. So these are the basic things that we have here. And there is one particular property which is neither extensive nor intensive, which is surface area, total surface area. Actually, if you calculate carefully, you'll see. Because normally in case of extensive properties, what you do? In case of extensive properties, if you have a total system of property X, now if you cut this into 2 parts, okay, so if you cut this into 2 parts, so let's say this is your first part having property of X1, and this is your second part having property of X2. This is X2. So this things X is actually extensive if X is equal to X1 plus X2. Like for example, you take mass. Okay, mass is extensive because if I take a 5 kgs block and if I split it into 2 parts, for example, say 2 kgs and 3 kgs, then if I add this 2 and 3, I'll get again 5. Similarly volume. Okay, similarly entropy. Okay, we'll see what is entropy and all in much detail maybe after 45 minutes. So this is what we have. In case of intensive, if there is a system and if the property is X, now if you again break it into 2 parts, for example, then clearly this is the first part and this is the second part of values X1 and X2. What you will clearly identify here is this X is same as X1 is same as X2. Like for example, if you talk about density, okay, now if I take a 5 kgs block of for example copper, say copper, if I break it into 2 parts and if I take densities of each block independently, the densities of both these blocks will be equal and the density will be same as the total block, correct? So that's why in this case, like for example, density of the total piece is same as densities of the individual pieces. Okay, so this is the way you can check whether a property is extensive or intensive. Clear? So this is the condition mathematically checked for extensives and this is for intensives. Okay, and when you talk about surface area, total surface area, like for example, if you have a sphere, this is 4 pi r square. Okay, normally if you have this. Now if I cut this into 2 parts, then this 2 pi r square surface area of hemisphere, this 2 pi r square is also there, but along with this pi r square, because there is a cycle here and there is a cycle here, so this extra 2 pi r square comes. So none of these 2 equations get satisfied in this case. Okay, so that's why we generally call this neither extensive nor intensive. Anyway, this is just some tricky question that some people can ask you in some interviews. Now once we talk about properties, I would straight away go, you all know how to calculate absolute pressures and all. I have taught you in fluid mechanics or in basic thermodynamics. Shivam sir might have taught you definitely. Like if you normally generally take any system, the pressure of the system can be talked with respect to 2 references. One is the absolute zero where the molecular motion dies, and the second with respect to the local surroundings, which is the atmosphere. Okay, and pressures which are measured with respect to atmospheres are called gauge pressures, and which with respect to absolute zero are called absolute pressures. Okay, now if you, I would straight away go to the thing. See here, initially how we try to identify the relation between properties. Okay, because you know P is one property, temperature is one property, which are generally important in our system. These 2 are measurable. Okay, these 2 has to be measured. Okay, volume also has to be measured. Now in the initial days, what they have done was, we have thermometers, of course, from 0th law of thermodynamics. 0th law of thermodynamics. This 0th law of thermodynamics is actually very powerful. This is the law which gave us the concept of thermometer actually. Okay, you all know what is 0th law of thermodynamics? Yes, come on, type in the chat box, everyone. Mohit, Nitin, Vivek, Ladani, Rahul, Ankit, Vishwadeep, Sunil, Suman, every one of you. Do you all know what is first law of 0th law of thermodynamics? Yes, correct. If two bodies are in thermal equilibrium with each other independently with a third body C, then all three are in thermal equilibrium. That's what it tells you. Okay, so this actually tells you, you all know this, right? Yeah. So if two bodies are separately in thermal equilibrium with a third body independently, then definitely these three bodies are also in thermal, means the first two bodies are also in thermal equilibrium. Okay, this gives us the concept of thermometer. The reason is, normally if you go to a hospital, what people do to test your temperature, normally nowadays we have digital meters, but in olden days we used to have a glass thermometer, which many of you might have seen. Melika Hatha, fantastic. Okay, deals the concept of thermal equilibrium. Yes, of course. Okay, 𝐂𝐤𝐴 deals with the concept of thermal equilibrium. Of course, thermal equilibrium, not thermodynamic, thermal equilibrium. Okay, now if you see, this 𝐂𝐤𝐴 gave us this important concept of that if two bodies has to be in thermal equilibrium with each other, they need not be in direct contact with each other. Normally what happens if you taste mercury, let us suppose if mercury falls on your tongue, it is very dangerous. Okay, but with the help of thermometers, what you are able to do, first when you keep thermometer on your tongue, the tongue and the glass of the mercury, the glass of the thermometer becomes in thermal equilibrium with each other, and the glass of the thermometer and the mercury inside will again come in thermal equilibrium with each other. So that's why finally the mercury in the thermometer can get the temperature of your tongue actually. Okay, so that's how thermal equilibrium is transferred from your tongue to the glass of the thermometer to the mercury. Okay, so that's how this 𝐂𝐤𝐴 law is very much important. Okay, and scale of temperatures, if you see, scale of temperatures, now which is nothing but your thermometer. Clearly if you have any scale, we'll have a freezing point which is normally called the ice point, and normally this is called the steam point, and any value x in between is written as ice point by steam point minus ice point, which is nothing but the range, total range with which you can get. So this is your ice point. So this has to be a constant for any thermometer, correct? So this has to be constant for any thermometer. So you design Celsius or Kelvin, whatever you do, definitely this equation has to get has to be equal. Like in case of degree Celsius, this is made as 0 degrees Celsius and this is made as 100 degrees Celsius. Okay, so that's why normally if you want to convert something in Kelvin, this is Celsius scale, and if you have the Kelvin scale, in Kelvin this is set to 273.15 Kelvin and this is set to 373.15 Kelvin. So something here, if this is y, then a reading of x in degrees Celsius is same as reading of y if x minus 0 by 100 minus 0 is same as y minus 273.15 divided by 373.15 minus 273.15. Okay, now clearly these two are hundreds, so y is nothing but x plus 273.15. This is how we actually convert the things in degrees Celsius to Kelvin. Clear? Sir, I didn't understand that thermometers are arbitrary. Yes, you can design your own thermometer with a defined ice point and steam point. Okay, that's why since it is arbitrary, there are plenty of thermometers. Okay, degrees Celsius, Fahrenheit, Kelvin, lot of thermometers actually. Clear? Fixing these numbers is not very much very much defined. You can pick these two numbers arbitrary. It purely depends upon to how many divisions you are dividing this scale. That's it. In these two cases, it is divided into 100 degrees Celsius exactly, but in case of Fahrenheit scale, it is divided to 180 divisions. That's it. Clear? In case of Fahrenheit scale, it is 32 Fahrenheit and this is 212 Fahrenheit, so it is divided into 180 divisions. Clear? So anyone can design a thermometric scale or basically a thermometer depending upon this. Clear? And now, meaning of arbitrary here means you can take these values as you wish. Okay, you can take these two values as you wish. Okay, like ये किसी restricted guideline नहीं है, इसको 0 लेने का and इसको 273.15 लेने का, ठीक है? You can choose them. Clear? Now, one important question that comes here is, what is this number 273.15? That's what we should know. Okay, why 273.15 is very special in thermodynamics? पता है किसी को? किसी को पता है कि क्यों 273.15 is such a famous number? Table point of water. Table point of water is not not 273.15 exactly. 273.16 actually. You know this? Table point of water. Normally, if you see, of course. Anyway, in case of we'll see pressure is actually 612 pascals and temperature is 0.01 degrees Celsius, which is around 273.16 Kelvin. This is what table point for water, of course. 273.16 is table point, not 273.15 actually. पता है किसी को क्यों 273.15 is very much important? लेकिन जब हम कैलकुलेशंस करते हैं पावर साइकिल्स में, लेकिन या कुछ प्रॉब्लम्स में, दिस 0.15 डजंट play much importance because 0.15 of 273 is not much. So just for simplicity in calculations, इस 1.15 को हम डिलीट करते हैं. ओके, सो सारी कैलकुलेशंस हम 273 से ही करते हैं, लेकिन 273.15 इंपॉर्टेंट क्यों है मैं आपको पढ़ाता हूँ. ओके, मैक्सिमम पॉसिबल कोल्ड टेम्परेचर, स्पेस में जाओ, -100, -373, -173 केल्विन. बॉइलिंग पॉइंट ऑफ अमोनिया, लिक्विड अमोनिया, बिलो 0 डिग्री सेल्सियस. All these things. Okay, so anyway, I'll just give you a hint. To get this point, I should talk about the concept of pressure. Okay, so see, what is pressure? Pressure, normally in fluids I have defined intensity of external compressive normal load. External compressive normal load or external compressive load. But anyway, when I talk about intensity, all this dot product, dot dA, all these things come. Now, let me talk about one thing. If you have a container, for example, okay, if you have a container with you, this is container. Normally, if you go to a bit of statistical thermodynamics, what happens? These molecules inside, whenever you have these molecules inside, as long as these molecules have certain temperature, these molecules don't sit silently. They actually move randomly. Okay, normally we have, as per kinetic theory of gases, which you might have studied in plus 12 or somewhere, kinetic theory tells you that kinetic energy of molecules is directly proportional to T absolute. Okay, you know, you might have studied K is equal to T by 2 RT, all these things in your. सर ज्यादा कुछ पढ़ा दिया क्या? अभी आया हूँ, नहीं उतना ज्यादा नहीं पढ़ाया, यहीं से फॉलो कर लो, ठीक है. Rate of change of momentum of particles, yeah, of course. Okay, so kinetic energy of molecules is actually proportional to absolute temperature. 12th में पढ़ा था आपने. So in kinetic theory, so when these molecules are moving, what happens? Let us suppose if I fix a pressure gauge here, which is showing some reading. Now, this pressure gauge will actually measure the pressure P of this gas depending on number of collisions acting here. Okay, so average number of collisions. This is very much important. Average number of collisions. I think it is COLISS, collisions. What is the spelling of collisions? I forgot. Collisions. Okay, we'll fix this. If there is some wrong in English, please forgive me for this time. So now, yeah, T is equal to K is equal to T by 2 RT. Yeah, 1.5 RT, of course. Okay, now anyway, if you see this, in this container, for example, kinetic energy is very much important, and kinetic energy is nothing but half mv square. Clearly, this v square, v is actually important, but along with v, this mass is also important, because let's say, for example, if I take out these molecules, if normally let's suppose if I break to some small extent here, if I connect a vacuum pump and if I start pulling out the air or any gas, whatever, if there are only 3 to 4 molecules inside, then definitely number of collisions act in this place over a given time. Let us say, for example, if I'm taking some 10 seconds of time, okay, within 10 seconds of time interval, number of collisions taking place here will decrease. Yes or no? If number of collisions decrease, then definitely this pressure gauge will definitely not show the same value, which we clearly know if you take out the gas using a vacuum cleaner, then definitely pressure will fall inside. Right? So this is basically due to the collisions, average number of collisions, and of course the velocity with which collisions are happening. Normally when collision happen, something gets transferred between two bodies. Let's suppose last few days back I have an accident, small accident. If two bodies collide, then what happens? Something gets transferred between the bodies. What is that? If two bodies collide, something gets transferred between them. What is that? Momentum. Yes, correct. So normally in a collision, momentum gets transferred from one body to another body, correct? So therefore, pressure depends upon, oh sorry, I'm writing with black ink on blackboard. Fantastic, genius. So pressure is it depends on molecular momentum transfer due to collisions. Molecular momentum transfer due to collision of molecules with container walls. With container walls. With container walls. Okay. So this is the main reason. Normally when collisions happen, so try to include Hindi also. Acha, theek hai. Are you all right? हाँ, मैं ठीक हूँ. ठीक है. So now see here. One thing that you know, pressure depends upon the molecular momentum transfer, and momentum depends upon linear velocity, and linear velocity depends upon temperature. Of course, kinetic energy depends upon velocity depends upon temperature. Okay. Now, when this velocity is depending upon temperature, can I say somehow this pressure and this temperature both are related to each other? Can I say both of them are friends? Yes or no? Because if T is high, definitely velocity of the molecules will increase. If velocity of the molecules is increasing, then when these molecules are colliding with the containers of the wall, the momentum exchange is high. If momentum exchange is high, this reading is high. Can I say this? Can you understand the connectivity between this and this? Yes? Now, one point I want to tell you. Somehow you know this P is proportional to absolute. Of course, I am talking only about absolute. Is proportional T. Let's say T is in degree Celsius. This is fine. So people know that. Sir, they say, please, इतने English समझने में time लगा है. ठीक है, I'll teach slowly. थोड़ा fast चलेगा क्या? ठीक है, अगर किसी को कोई दिक्कत है तो immediately आप chat box पे type कीजिए. I'll do accordingly. Okay? अगर slow करना है तो मैं slow करता हूँ. दूसरा बार explain करना चाहता हूँ. I'll do it again. Fine. Now people know this, pressure and temperature are friends. Okay. Now what is the relation between them? That's the point of interest. So when you don't know maths, one thing that you should always do is experiments. Correct? So what they have done is, look, they have taken a container where the gas is at some T degrees Celsius. Before doing this, tell me one thing. There are two lines. And you want to do some calculations. Okay, you want to do certain calculations. Out of these two lines, which is easy for you to do analysis? I'm asking my question again. Out of these two lines, which is easy for you to do analysis? First one or second one? Let's say I want to do some integrations and then that this everything. Okay, so out of these two, which is easy to deal with? Undoubtedly second. Correct? Okay, keep it in mind. Now, this gas also has some pressure. They know the volume of the container, V. Okay, volume of the container is also known. Now what they have done is, they have taken the temperature axis and also pressure axis. Volume is known, and with a simple pressure gauge you can calculate what is pressure, and by putting a thermometer you can also calculate what is temperature. Okay, P is known, T is known. Now what people done, for a gas they observed that P and T follow this trend. Okay, like if you keep plotting pressure versus temperature, as temperature is increasing, pressure is increasing, it is clearly known, slope is positive. Normally if you take the angle theta is less than 90, so tan theta is positive, slope is positive. So this is what they have observed for one of the gases, gas 1. Now gas 2, they have changed the gas inside the system. Now clearly for the same temperature, pressure may not be same because mass of the gas molecules will be something different. Okay, now they have taken something like this. They got some curve like this. So this is for gas 2. So this is for gas 2. Similarly, they have plotted for different gases. When they plotted different gases, they found one interesting point. If you extend all this stuff, these two lines are intersecting at one point. There is another gas which actually looks something like this. So this is gas 3. Gas 3. So when they plotted these things, they found one thing in common, that if you extrapolate these lines, all these lines are meeting at one particular point, and if these lines are meeting at this point, the meaning is at this particular temperature, this P absolute is 0. Okay, so P absolute is 0. So does temperatures below absolute temperature exist? Space. Okay, so you can see this is 0. At this particular temperature, if you extrapolate this line, that means you came to know at this particular temperature, these curves, all these curves are touching 0 pressure. That means at this particular temperature, there are no collisions that's happening inside, which means molecular motion stops. Clear? So at this particular temperature, whatever might be the temperature, at this particular temperature, there is no pressure. Means if you just go back to the story, if there is no pressure, no collisions here. What is the meaning of no collisions? All molecules are sitting silently inside. That's it. They're not moving. Okay. So this value, when they measured with scale, this value came out to be minus 273.15 roughly. This is how they identified minus 273.15. At that particular temperature, where absolute temperature is 0, there is no motion of molecules and all the molecules are sleeping silently. Okay, so therefore this temperature is there. Now if you see one thing clearly, if you know this P absolute is proportional to T, you came to know that these are linear equations roughly. So if you want to relate y and x, P absolute is equal to, this line has some x intercept, so A into T degrees Celsius minus plus 273.15 degrees Celsius, correct? Because you can clearly see this is constant A, plus or minus. Normally if you see, if you put y is equal to 0, then x is equal to negative. Yes, correct. So this is the equation which it came. Okay, because clearly this value is the x intercept. Okay, so 273.15 is the x intercept. Now since this is always giving you this form, but you know it is easy to work in this form. If you want to have this intercept 0, you should shift this origin from here to here. That's it. Correct? Yes or no? Type in the chat box. You should actually shift this origin from here to here. That's how you can make this equation from this to this. Logic, no? Maths, simple maths. Correct? Will all of you agree with me? Yes or no? So there is my follow-up question. If molecules are at absolute rest, at absolute 0, how can they be lower temperature? How can molecules have motion slower than rest? Look, it's known that at 0 they'll all stay at rest, but it doesn't guarantee that if you decrease the temperature much below, still they can stay at rest. Molecules may become cool and cool, that's it, without any motion. That can happen, no? Clear? So how to find constant A? Easy, yeah? Just at this particular point, you know these two values. You know pressure, you know temperature. Put in this equation, single unknown. You'll get A. That's it. Okay, Panit? Look, at 0, molecular motion stops. But if you further decrease the temperature, the molecules will get cool and cool. I mean, they'll feel colder. That's it. Nothing much. Clear? Okay? So that's why this Kelvin scale, because this is in absolute, these guys want to make this temperature also in absolute. That's why your T absolute is nothing but T in degrees Celsius plus 273.15, which you can easily understand, of course, from scale of thermometers. Also, let's say when this is 0, this is 5. Then if I shift this to minus 273.15, this 5 becomes 278.15 clearly, because this origin has moved by this much amount. That's why we add 273.15. That's it. Okay. Look, there are few locations in space where temperature even goes to minus 200. Okay, which is like, acha, you're talking about it's in degrees Celsius. Okay, so minus 273. Acha, okay, minus 200. Correct. Yeah, this is correct then. Minus 273.15 is the 0 absolute. Okay. But I think people started approaching these values, okay, because there were few instances in space, I mean in the outer space, not within the atmospheric level, outside in the outer space. I think people found temperatures which are much than this. But anyway, in our thermodynamics, we'll generally talk about this range, okay, because all we do is power cycles, okay, that's what. Clear? So anyway, this absolute scale of temperature is the main discussion here. This is how it is generated, because it's relatively easy to work. Okay. Now let's see what happens in a gas normally. If you have different gas molecules, then clearly these molecules will interact with each other, correct? Because normally if you see in case of gases, there is something called Knudsen number, which I think, did I tell you this in fluid mechanics, or I did not teach you? Okay, fine. If I didn't teach, you can learn here. There is something called Knudsen number, and it's normally called, I don't know how you guys pronounce it, but it's normally called Knudsen number. So what is this Knudsen number is basically, this lambda is called the mean free path. Okay. So what is mean free path? Distance traveled by a molecule between two successive collisions. Okay. So distance traveled by molecules between two successive collisions actually here. Now, normally if you have this like molecules, normally let's say if you have two molecules, these molecules generally attract each other because the spacing between them is long. Okay, yeah, continue my assumption. Now let's get back to the story to some extent. If you take these two molecules, for example, normally in case of gases, molecules are loosely packed. You know, generally the distance between two molecules is large compared to the atomic radius. Now when these molecules are large comparatively, the nucleus of this molecule will attract the electrons of this molecule. Similarly, the nucleus of this attracts this. So these two actually come close to each other. Once they come close enough, the electron pairs on the outer electron shell, they start repelling each other. So anyway, in general, normally during the movement, when the molecules are not in very much contact with each other, the general molecular forces of attraction, the general molecular forces are attractive in nature. Okay, so these two molecules generally they try to attract each other. Now we do something called ideal gas analysis. So what is this ideal gas analysis? Let's see. If you have a container, again of some volume, say V, there is some gas in this, things are like this, there is some gas in this, and there is certain pressure, also some temperature. Now what we do is, generally, if you observe this quantity, limit P tends to 0. If I am telling P, it is absolute always. Okay, so please keep that. If you check this for different gases, N is the number of moles of gas. Number of moles which you can easily identify. This is number of moles which you can easily identify from mass divided by molecular weight. Okay, so mass divided by molecular weight. Pressure you can measure, volume you can measure, T you can measure. Now one thing that happens is when P is actually very small, this value tends to a constant value actually. This is again calculated from experiments. If you take this value, this is P absolute, and this is PV by NT. Actually, for different gases, what happens is different gases behave this way, but when P absolute is coming very small, all these gases will tend to some constant value, and this value is nothing but your constant, which is Ru. Okay, which is 8.314 kilojoule per kilomole Kelvin, which again if you measure with scale, this value is 8.314, which the values accordingly you have the units. Okay, sorry, the units you have depending on kilopascals, meter cube, kilomoles, Kelvin, all these things. Okay, there is some question, but the temperature itself is due to movement of molecules and collisions, right? Movement of molecules is due to temperature. Okay, not the converse. Okay, Panit? No, it's okay. You, whatever doubt you have, you can always ask me. Okay, movement of the molecules is due to the temperature. Temperature is not due to the movement of molecules. Clear? Movement of molecules is one consequence of temperature. That's it. Because kinetic energy increases. Clear? Normally, even if you take crystalline substance, pure crystalline substance, what happens when you start heating it? Lattice vibrations, the amplitude of the vibrations increase. Okay, and if the molecules are free, they move. That's it. Clear? Now, anyway, if you see, this is 8.314. So that's how we have PV by NT is equal to this constant, which is constant for any gas, because this experiment is for gas 1, gas 2. So whatever the gases you take, this constant is coming same. So this is denoted with Ru, which is called universal gas constant, and we have PV is equal to NRU into T actually here. Now, one very important assumption that we should make here, when we are writing this equation, we made two things unknowingly. What are the two things? In this V, this is V. What is V? Generally we are substituting. This is V, correct? So this V is volume available for movement of molecules. For movement of molecules. Volume available for movement of molecules. This is what we have considered. In this equation, if you are calculating PV by NT, we have taken V as volume of the container. So that's one thing that we made. But physically what happens, this, let's say for example, if you take this molecule don't have this complete V to move, yes or no? Because some part of this volume is actually occupied by its friends, yes or no? Because if you have a volume of V, you know, generally within that volume, molecules are loosely packed. So maybe here one molecule, here one molecule. There are plenty of molecules like this. Now clearly what happens, at every point there is no molecule. This is 100% clear. Okay, I'm just telling you, repeating, see carefully. if you fill gas in this container, molecules are not present at each and every point in that particular cylinder. Yes or no? If they are present, it will become a solid. Yes or no? Molecules are not very closely packed, they are very loosely packed in case of gases. Okay. Now, this V what you are writing is actually the volume available for the movement of these molecules. Understood? Yes? Can you get the difference? This V is not the volume of molecules. Volume occupied means volume available for the movement of the gas. Clear? Okay. I कुछ समझ में आया या नहीं? Type कीजिए ना chat box पे. Okay. Now let's see. That's one assumption that we made. Now when we are using V in this formula, undoubtedly you will definitely put the volume of this box or volume of the container. If you are putting volume of the container, you are neglecting one thing. What is that? Means you are telling for the movement of this molecule, this complete V is available. That's what you are telling if you are putting V here. So unknowingly you are actually neglecting one quantity. What is the quantity you are neglecting? Volume of molecules. Yes, exactly. We are neglecting volume of molecules, and we are telling for each molecule or the complete volume available for the molecules to occupy is this capital V. That's what we are telling. Yes. Volume of molecules are being neglected if you are writing that capital V there. Yes, volume of the other molecules is neglected, correct? So this is one assumption we make when we are writing this equation. Clear? Means if you are substituting capital V as volume of the container, that means the assumption that you are making is neglect the volume of molecules. Clear? So in this, which is ideal gas equation, one assumption that you are making is neglect volume of molecules. This is what one you are doing. Next, you can understand one thing. In this graph, or basically this fellow, P tends to 0. Actually, there is something called reduced pressure, PR tends to 0. We'll see what is reduced and all when we go to pure substances. Okay. Now, at this particular point, I want to tell one thing. P absolute very close to 0 is same as P reduced close to 0. I'll tell you why later in a bit. But when P absolute is very close to 0, that means, let's say for example, I started measuring pressure here. At this point, if pressure is actually very low, that means the collisions are not very effective. That means at this point, the number of molecular collisions happening are very low. So that means molecules are moving inside very loosely. Okay, so that means if pressure is low, I'm not talking about temperature. Okay, temperatures, it can be high, low, anything. Maybe molecules are going fast or molecules may be going slow. That's a different story. But number of collisions happening at this place is actually low. If number of collisions happening is very low, practically that means number of molecules present in the system is generally low. Correct? That's why similarly we can successfully make an assumption volume of the molecules is neglected, because when pressure is very low, the molecules or the number of molecular collisions happening at this place is low. That means practically number of molecules hitting that spot is actually less. That means number of molecules present in this system is generally low, practically. Okay, so if that's the case, we can actually neglect the volume of molecules. And also if molecules are very loosely there, means let's say one molecule is here, second molecule is here, then that means when these two molecules are separated by some good enough distance, number of available locally are low. Yes, correct. Sir, doubt. Yeah, Aniket, you can ask. Okay. So if this is far, normally these two molecules will have certain intermolecular attraction forces, correct? They'll try to attract each other. But when they are moved far away, as per your statistics again, F is equal to force of attraction, G m1 m2 by r square, all these things, and also electronic forces, Q1 Q2 by r square, where this is permeability, all these things. If you go to a bit of statistical thermodynamics, this distance between the molecules is very large. Okay, if distance between the molecules is very large, what happens to the intermolecular forces between the molecules? What happens to the intermolecular forces between the molecules if this number is very, very high? What happens to the intermolecular forces? Not zero, but very low, correct? Very low is what we can say. Okay, not perfectly zero, but it is very less is what we can say. So in this actually tells you that Under these two conditions, the gas is called as ideal gas, and this is the equation for ideal gas equation. That's it. Okay, so that's what we have. Clear? So anyway, this is the ideal gas equation under these two assumptions. So, but in actual cases, the number of gas molecules are not very low, they are actually very high. Let's say, for example, if I fill oxygen, okay, you all know Avogadro number 6.024 into 10 power 24, all these things. So practically, if you take any system of gas, the amount of molecules which are present are drastically high. Okay, not just not just like we have some small number of molecules, we have plenty of number of molecules. So that's why practically every gas, when you analyze, it shows certain deviation from this behavior. Clear? Because this P tends to 0 is no more valid, and also this cannot be neglected in actual case. Understood? Because even if you put some 10 grams of gas in any system, 1 kg consists of 6 into 10 power, 1 mole consists of 6 into 10 power 23 molecules. For example, if it's oxygen, if you divide 6 into 0.23 into 10 power 23 by 16, that 10 power 23 becomes hardly 10 power 21. That's it. Okay. And if you put only 10 grams, that 10 power 21 becomes 10 power 19. That's it. Okay. 10 power 19 is still large number of molecules which can make significant impact. That's why every gas in the realistic case will actually get deviated from ideal gas behavior. Clear? Okay. Yes or no? Someone asked there is a doubt, no? Someone told no. Aniket, yeah, you can ask your doubt. Is it clear to all of you till this point? This is valid only under these two cases. Otherwise, it's not valid. You cannot use this. Okay? Because you basically used this from P. P tends to 0 at low pressures. Can you say that about that condition? At high temperatures and low pressures, all gases are ideal. But my question is, can you say about that condition? Okay, that is one question. Second, but my question is, T more collision and result in less intermolecular distance, so intermolecular forces may exist. Look, I'm telling you, the temperature may be high, the velocity at which the molecule is striking is high, but as long as number of collisions are less, it doesn't matter even if a single molecule is going and hitting it high, average number of collisions in a given time falls down. Clear? Why volume of molecules is not considered? Because we are practically saying that the number of molecules are very low. Okay, and also the size of the container. In general cases, what happens? Size of the container is very much large when compared to the volume of the molecules. Okay, like for example, you see volume of each radius of each molecule is like 10 power minus 10 power minus 15 Armstrongs. Okay, normally Armstrongs are the suitable units. If you do square of that 4/3 pi r square, all these things, then volume of molecule becomes very, very small. Even if you multiply with Avogadro number, this it comes only to some portion of this particular gas. Okay, my question is, more T, more collisions. Look, I'm telling you one thing. Basically your question is, let's say this molecule is going very fast because of high temperature. Let's say this T is high, this molecule is going very fast, so why pressure can be low? That's what your question. Pressure doesn't only depend upon this velocity of a single molecule collision, but it depends upon the number of collisions. Okay, when molecules inside the system are less, then definitely number of collisions will be less. That's how your pressure is low. Clear? Not because of your single molecular velocity. Okay, Ladani, I'll come back to your question at high temperatures and low pressures, all these things, just in a minute. But is it clear to all of you till this point? Okay. Now understood, right? Okay. Now coming to this question, at high temperatures and low pressures, all gases behave as ideal gas. Okay, fine. How many of you have this question? How many of you had this doubt actually? Because even when I teach offline classes, generally people don't understand this high temperature and low pressure combination. Because you can understand clearly, if T is high, generally it is expected that molecules are striking at higher velocity, so P is also high. But what is this combination of low pressure and high temperature? Do anyone know? Yeah, I'll just, am I going too fast? Is it clear so far? Going cool so far as of now? Okay, now let's see one important thing about your question. There is one important thing which is called compressibility factor. which is called Z. And what does this compressibility factor actually tells you? Measure of deviation of gas from ideal gas behavior. From ideal gas behavior. Okay, so from ideal gas behavior. So it's same as external air when moved very fast from local air, where air displaces locally, creating pressure decrease, which is starting the fact that number of available molecules of air displaced. So I didn't get you per much. It's a long statement. Just a minute. So it's same as external air when moved very fast. Generally, when you move very fast, your air gets streamlined out, where air displaces locally, creating pressure decrease. Yes, correct. In front of your mirror, there's slight pressure less, because you can see whenever you're standing near a fast moving train, you might have observed. Okay, let's say a train is moving very fast and you stand closely to it. You will feel the pressure in this location is generally low and the pressure behind you is large, and generally you'll experience that the train is pulling it towards the train. You might have seen this, correct? Yes, correct. Whenever the velocity or the number of molecules are getting diverted, then definitely pressure falls in that locations. Okay, clear? Now, anyway, let's get into this compressibility factor. So what is this compressibility factor? Is actually the actual PV by NT by this PV by NT when this pressure is low. That's what. Okay, means if you take a gas, like for example you take n moles of gas, suction is created. Okay, so that's what. So if you see in this case PV by NT, normally if you take some amount of mass of gas, you know, molecular weight, so mass by molecular weight gives you a number of moles. N is known, T is known, P is known, V also you can know. So actually if you see this PV by NT divided by limit P tends to 0 PV by NT, and here one actual thing that you should know is this V is actually V actual. Okay, because it's no more an ideal gas actually. So this V, what you're substituting, is actually V actual. So Z talks about this ratio, and this ratio, if it's 1, then the gas is exactly an ideal gas, but actually generally values are less than 1 or more than 1. Okay, so that's why this two, volume here and volume here, is not same, because here you cannot take volume as the volume of container, it's the actual volume. Okay, so anyway, if you see this, Z is equal to PV actual by NT divided by, this can be taken as universal gas constant RU, so it becomes NRUT. So P times V actual is equal to Z times RUNT. Now from ideal gas equation you can do one thing, you can replace this combination as P into V ideal, correct? Normally the gas is occupying the volume occupied by the volume occupied by the gas in ideal conditions is what you can do. So P times V actual can be written as Z times P into V ideal. So clearly P, if you eliminate them, Z is the ratio of this V actual divided by V ideal. For majority of the gases, this value is always less than 1 generally. Okay, I don't say exactly less than 1 for all the gases, because there are some monoatomic like hydrogen and helium are exceptions, but in general if you see, this Z can be written in this form, where Z is the compressibility factor and this is V actual by V ideal. Clearly, you know, when you're talking in the ideal conditions, volume occupied by the molecules is the complete container, so definitely V ideal is large in general cases. Okay, so that's why for real gases, this Z is less than or greater than 1 generally. For ideal gases, Z is equal to 1. For ideal gases, Z is equal to 1. Clearly in this equation, if you put Z is equal to 1, in this equation if you put Z equal to 1, PV is equal to nRT, that's what you will get. Okay, for ideal gas it is 1. Yes, this is what you will get if you put Z equal to 1. This equation is nothing but your ideal gas equation. Okay, that's what you have. So anyway, this Z is the deviation from ideal behavior. It shows in two different ways. Now one thing I want to tell you, there's something called compressibility chart. Okay, to answer that question, someone is asking high temperature and low pressure, what happens here? We have something called compressibility chart. Compressibility chart. Now in this compressibility chart, you have Z here and PR, where PR is called reduced pressure, P by P critical actually. Okay, you all know what is critical pressures and critical temperatures. Normally if you take any phase change of a substance from liquid to gaseous transition, the dome actually closes at the top point, leaving a point of inflection, correct? What happens in case of hydrogen and helium? I'll tell you. In case of, so please teach only one exam, pattern basis, because we all are having very less time. Pakka, I'm telling you. It's not PhD, it's all, look. Avi, I'll tell you one thing. Do you have PYQ book of gate mechanical? PW's book, this book, yeah, luckily it's on my floor. Yeah, this book. Do you have this? Yes or no? If you have this, I suggest you one thing. Try to open thermodynamics questions. You will somehow find out you need all these points. Okay? Yes. Many of you will be writing 𝐂𝐸. In 𝐂𝐸, in mechanical syllabus has no much variations. You need all this. Do you remember in 2021 also there came a question based on compressibility factor? You know this? 2021 or 2022? Which year, guys? Let me check. Book is here now. Why to go for other things? I'll open this book meanwhile. Thermodynamics, page number 5.1. Okay. 5.1. Let's check. 5.1. Here. There's a question 2022 or 2021. I don't remember exactly. Where is this? I think 2022. Yeah, 2022, I guess. There's a question. Bombay 2021. 2021. Z is asked. Yes, 2021. Sorry. Yes. Z is asked. No. Okay. So everything what, look, I'm telling you. If I want to teach complete thermodynamics of fluid mechanics or heat transfer, what I know, I need minimum 150 to 200 hours per each subject. Okay, but that's not the point. You should actually, many people put some, you know, what do you say, some wrong inception in your mind that GATE is a very complicated exam, but actually GATE is a easy exam. Okay, we should never try to increase the syllabus. Whatever is there, just teach that. Okay, fine. Let's see. So what is this PR? So normally, you know, whenever there is a phase change happening, you know, this liquidus line and the basically this fusion curve and the vaporization curve, they both meet at one particular point. Okay, so that's called the point of inflection and also critical point. The pressure temperature corresponding to that point is called critical pressure and critical temperature. Normally for water, you see P critical is around 220.06, yeah, 221 bar, and T critical is 374 degrees Celsius, roughly 375, some books write 374. What happens here is, because this statement at high temperatures and low pressures, gases behave as ideal gas. To understand this statement, it's not very simple as you write this. Okay, behaves as ideal gas actually. Ideal gas. Okay, see. Many people have the misconception that a gas is maintained simultaneously at high pressure and low temperature. Sorry, high temperature and low pressure. No. This statement you should read properly. There is a comma here, at high temperatures or at low pressures. That's the meaning of this. This is called P reduced, P by P critical. If you see, the curves for different gases comes out like this. This value is 1. You might have seen this graph. Normally if you plot PCR and Z, from this equation, if you calculate, for gas 1, it comes out something like this. For different gases, it comes out like this, and it starts like this. These different curves are for this. Okay. So, which means you can understand clearly, in this junction, in this region, when PR is tending to 0, because this is the 0 axis, if this is PR coming to 0, that means this quantity is also tending to 0, that means P tending to 0. When P is tending to 0, low pressures, when P is tending to 0, one thing that you can observe is, irrespective of the temperatures, TR is nothing but T by T critical. Okay, So TR is nothing but T by T critical. At this point, you can see, irrespective of the temperatures, all these points are coming and getting mixed up at Z equal to 1. Can you observe this? In this graph, this is normally called the compressibility chart. In this compressibility chart, as your PR is approaching 0, that means this P is tending to 0. All these graphs are coming and merging at Z equal to 1. And if Z equal to 1, that means all gases are approaching ideal behavior. Okay. And also, you can understand one more point. Actually, I have drawn some wrong in this diagram. These variations, just for your understanding, I have drawn very large, but actually they become very straight like this. Okay. Which means at higher temperatures, TR is actually this much. Okay. So T critical for water, if you add 273, this is like almost 747 Kelvin. Okay. So this is like 747 Kelvin. When TR is equal to 2 and TR equal to 3 at these points, like if this is like 1400, 1500 Kelvin, at that temperatures, what happens is these lines are generally flat. Okay. It's just for your understanding, I have drawn them inclined, but these lines, when you go for higher temperatures, they become almost flat. And at any pressure, when this, let us suppose if this line is flat like this. Okay. If this line is flat, whatever the pressure you take on this line, Z values will be very much close to 1. Yes or no? So Z values will be very much close to 1. What is T in TR formula? Temperature. That's it. Okay. This is the actual temperature. This is the critical temperature. This is the normal pressure. This is the critical pressure. That's it. Clear? You can understand. In this line, when this line is almost like flat, then clearly whatever is the pressure you take along the x-axis, the Z value will be very much close to 1. Can you understand this? Yes or no? Yes or no? Yeah, TR is reduced temperature, correct. TR is the reduced temperature. These are actually normalizations with respect to critical values, that's it. Like how I have done normalization in boundary layers when I'm doing scaling analysis, similarly here for pressure and temperature. Okay, so that's why these two statements would, at high temperatures, because of flatness, at low pressures, all these meet at 1. Because of these two reasons, the gases behave as ideal gases practically. Okay, did you understand this statement? This one, sorry, this statement. Okay, anyway, it's already 1 hour, so I'll just move fastly. So anyway, all this is what you have. So one thing that you understood, in practice, volume of molecules should be considered. Secondly, intermolecular forces should not be neglected. Okay, now important point that you should know is, you have gas molecules. आपके पास gas molecules है. Volume of the container is V. If you actually take the gas, pressure of the gas, if the gas is ideal gas, your equation should be nRUT divided by V. Correct? That's what your equation has to be. Actually, if the gas is ideal gas. But in actual cases, the gases are not exactly ideal. They actually change. So first thing that you should do is, volume of the molecules has to be taken into picture. Means if this is volume V, let's say for example volume of molecules is there, then actual volume that the gas can move inside is only V minus V of the molecules. Correct? If the actual volume available for the movement of molecules is V minus volume of the molecules, from this quantity we have to subtract some positive number. That positive number is normally denoted as N times B. This B depends upon what are the units you are taking. This is one reason. One assumption is volume of molecules is neglected. Now I'm not neglecting this. So in graph, sorry, didn't get this. So in graph, okay, one term is 0 less than P reduced less than 7. 7? Where it is? 7. Sorry, didn't get you. One term is written as 0 less than PR less than 7. So beyond that, variation may get different. Normally, in actual cases also, we'll generally go up to the range PR is equal to 2 or 3 maximum. Beyond that, things change. Atomization happens and molecules get dissociated. Okay, it's like a rupture. Normally, let's say if your mom make you biscuits, okay, you put all the biscuits in one container and start pressing them very high. Then what happens? They break up. Okay, so after some point, things change. Clear? This is what you have. So this correction, what we are making in this equation, NB is actually for van der Waals equation. 1 minute, let me tell you. Okay, बहुत दिन के बाद thermodynamics पढ़ा हूँ मैंने. I'm teaching good, okay, fine, because it's been, I think lastly paid batch thermodynamics happened in May, I guess. Yeah. Okay, so anyway, let's get here. So P gas is equal to nRUT divided by V minus NB. This correction firstly you are making for the volume of molecules. There is also second reason, intermolecular forces are actually, you know, neglected here in this case. Here, in this case, intermolecular forces are neglected. If intermolecular forces are actually present, as I told you, generally in case of gases, molecules are loosely packed. So in general, the force of attraction between the molecule, the intermolecular forces are attractive forces. Okay, molecules try to attract each other. Tell me one thing. You have one molecule here. You have one molecule here which is about to collide like this. If this molecule is actually attracting this molecule, what happens to the pressure here? So English की speed तेज है, ठीक है, मैं थोड़ा सा आराम से पढ़ाता हूँ, ठीक है. So see here, these are two molecules. In actual case, these two molecules are attracting each other. So if this molecule is trying to attract this molecule, what happens to the pressure at this point? What happens to the velocity at which it collides? It will decrease or increase? It will decrease or increase? Decreases, correct? So that's why from this term we should also subtract one more term, which is an square by v square actually. Okay, so this exactly this derivation of how this n by v is coming, that is again a separate story. You have to go to statistical thermodynamics, but right now I'm just showing you this correction is responsible for the account of volume of molecules. This correction is responsible for the intermolecular forces. Clear? Now if you simplify this equation, we have, if you just keep this as p plus an square by v square into v minus nb is equal to nRu into t. If I write this equation like this and if I tell you this is that and all, you will never understand. I'm clearly telling you this correction is for volume of molecules because I'm subtracting it from capital V. From this complete quantity, I'm again subtracting some positive quantity because of intermolecular forces. If you simplify this, this equation comes. Actually, this is how Van der Waals gave his equation, not this. Clear? This is for mathematical simplification because we are habituated to write PV equal to nRT. Okay? Why I'm talking all these things is because in applications of thermodynamics, we'll talk about a lot of places where we talk about adiabatic process, ideal gas equations, all these things. Okay? That's why. Clear? So anyway, if you delete this n, if you try to delete this n, you can write this P plus A by V by n, molar volume, specific molar volume. If you take one n out, we have V minus B, and this n and this n, if we get cancelled, it becomes Ru into T. So this equation is normally denoted as Van der Waals equation. Van der Waals equation. Okay. We remember day where this equation derivation has asked in university exam. Okay. Fine. Okay. So this is Van der Waals equation. So basically there are plenty of things we can do with this equation. But anyway, in our case, we always love to do the things simple or love to do the simple things. So we generally don't go for this equation, and we everywhere when people ask you to do something good, you say assuming ideal gas, so that equations get easier. Correct? That's what we do. Anyway, this is what we have. Now even we'll see the first law of thermodynamics. Okay. What is B, sir? Constant. Okay. So small v, please once again. Yeah. I'll here. This small v bar is nothing but molar specific volume. Normally you know this small v, specific volume, correct? Specific volume. This v is volume divided by mass, meter cube per kg. This is molar specific volume. Specific volume. Normally this is nothing but v divided by n, which is having the units meter cube per kilomole. That's what. Okay. I thought of talking about non-ejecting mixtures also, but I think time is short. We have to see first law, second law as well. So I'll teach non-ejecting mixtures, how molecular weight of mixture is calculated, everything in air conditioning. Okay, because in air conditioning, in moist air, we have two parts. Why I'm telling all these points here is, guys, look, I just you know, I can just write equation Q minus double equal delta U. In fact, I need not do that also. I can start air standard cycles. What is air standard? I can start. But when I'm doing air conditioning, normally, you know, water vapor cannot be taken as ideal gas. You know this, right? If water vapor can be taken as ideal gas, there is no chapter in your book called properties of pure substances. Yes or no? Let us suppose if I can use ideal gas equations for the vapor. You know this, no? Let's say in this region, if I can use ideal gas equations, no need of studying something called properties of pure substances actually. Yes. But so actually this and ideal gas both are different. But do you remember when we are doing psychometry, air conditioning, some of you might have already gone through in your engineering. If you are studying psychometry, for calculations of water vapor, we directly use ideal gas equations. Have you seen this? Yes or no? When you are doing some property calculations of moist air, we treat dry air and also water vapor as a mixture of two non-reacting ideal gases. And we do the analysis, whatever enthalpies, all these things you calculate based on that assumption. Okay. If you know water vapor cannot be treated as ideal gas, but at that time, very low vapor pressure. Yes, exactly. Okay. So you will see at this point, you know, water vapor cannot be treated as ideal gas, but in air conditioning, you actually treat water vapor as ideal gas and you do the equations. Why? Because water vapor sits in this locality. That's why. To make you understand those points, I am dealing these points. Okay. Nothing and nothing I'm going to teach out of syllabus, and pakka I'm 100% sure after the completion of syllabus, you cannot find even a single topic which I have taught out of syllabus. Okay. But definitely I'm going to cover 100% of your syllabus. That I can guarantee. Okay. Clear? Fine. Let's see. So anyway, first law of thermodynamics, I'm going a bit quick. Okay. So this is basically law of conservation of energy. Law of conservation of energy. Like if you have a system and if you have surroundings, of course, the surroundings which are very close to the system are called environment. All these things are there. But anyway, I'm just talking about the generalizer things. So you have surroundings. When you have surroundings, then clearly, let's say some energy is going in, wait, and energy is going out. One thing that all of us know is nothing but energy flowing in minus energy flowing out is nothing but change in energy of the system. This is what we have. Correct? That's your first law of thermodynamics actually. Clear? Is this clear to all of you? Okay. Now, see one thing. Normally, if you take a system, for example, I want to ask you one thing. I have taught you this hydraulic machines, na? Good. Let me ask you one small question. Let's say there is some gas or some liquid, whatever. Some system is there, some mass. It can be gas or liquid, whatever. Let's say you have this blading, for example, okay? This blade, turbine blade, some water, okay? This is a water. This can be gas also, doesn't matter. It can be gas. Basically, some fluid is there, okay? If I keep this water here, will this water rotate? मान लो कि मैंने इस water को यहाँ लगाया. Will this water rotate? No, correct? Will this water rotate if I keep it here? No, it won't rotate. We know this. Now let's say if I keep the same water here, if I keep the same water here, if I keep this water here, then will it rotate? नीचे लगाना पड़ेगा, हाँ करेक्ट. अगर मैंने यहाँ रखा तो डेफिनेटली इट विल रोटेट, करेक्ट. What do you think is the difference in these two cases? Don't tell in first place it is here, second place it is here, okay? What is the physics behind it? Why the water is able to rotate? Any idea? Any idea? Kinetic energy and perceives more. Momentum change. Okay, fine. You have your reasons. Definitely this fluid has temperature more than 0 Kelvin. So clearly here also molecules will actually move. Molecules will go and hit this blades. Here also molecules are moving effectively in one direction. It actually rotates in this case, but here there is no rotation. The reason is, in this case, whatever is the energy transfer or momentum transfer, what are the words you used, that is not in organized form, correct? Let's say for example, if some molecule is trying to hit this in this direction, there could be some other molecule which may try to oppose it, okay? So here, in this case, the energy is actually unorganized. But here it is organized. This kinetic energy what you have is called macroscopic kinetic energy because there is some bulk movement of the fluid. Here also the molecules have certain kinetic energy because molecules never sit silently if temperature is more than 0. At that point, the molecules have certain energy, they have kinetic, rotational, lot of energies, but they are not in organized form. Clear? Is this point understood to all of you? I want to make you understand one different point here. Many times when I write kinetic energy in steady flow energy equations, and normally if I am talking about later turbines, pumps, all these things, if I am doing some steady flow analysis, this kinetic energy is what we write as this bulk kinetic energy, not this translational kinetic energy. Clear? Let's say for example, if I am applying steady flow energy equation, V1, let's say if a fluid is coming in with a velocity V1, we are writing the macroscopic velocity of the system, not the individual velocity of the molecules because of this temperature. Clear? That has to be understood. Sabko clear? Okay? Yes or no? Clear? Now let's see. Anyway, if you come back to this, in general any system has macroscopic kinetic energy. When this complete system is at some elevation from ground, it has macroscopic potential energy plus. Now this system has also got certain velocities, like for example, if each molecule moves at a velocity v, okay, so here also each molecule moves at a velocity v. So when you take the molecules by themselves, there are some forms of energy, like if you look at microscopic, means if you look into this microscopic nature thoroughly, you will understand molecules have kinetic energy, which is molecular, microscopic, potential energy, microscopic. Then because of vibrations, it can have certain lattice energy, thermal energy it can have because of temperature, lattice energy. So we have sum of lot of energies actually. This sum together is actually called, because all these energies are laid within the system, they are called internal energy. Clear? When I am talking about the independent movement of molecules, that energy is already counted in this U. Clear? When you go for steady flow analysis, along with this, we also have something called flow work. That's why a plus PV term will come. Okay, U plus PV, which is enthalpy, which I think Shivam sir might have taught you in open system analysis clearly, or control volume analysis. You have U plus PV, but in this case, the flow energy is not there. That's why PV is not there here. We have only U. So this energy of the system is equal to kinetic energy macroscopic plus internal energy U is what we have. Clear? So that's what you have energy for the system. Now when you talk about the first law of thermodynamics for closed systems, for energy systems, I mean for closed systems, let's see what happens. And also if they are stationary, closed systems, they are stationary. Flow energy not there. Fluid is flowing, then why flow energy not there? Of course, here it is there. Like normally I'm just telling for closed systems, okay? Don't take this actually, okay? I'm talking somewhere in such kind of devices like this, okay? Not flow, okay? This is whatever I have told, this is only for closed systems, okay? Now let's see some things here. So for closed systems actually, guys, just a minute, I'm talking about microscopic, right? Yeah, we'll see the PV combination, but flow work is not there here as of now, okay? So that's what you please assume. Now here, for closed systems, stationary systems, if you see, the first law gives you energy in minus energy out is equal to change in energy of the system. This is first law of thermodynamics. Now you know, change in energy of the system is nothing but change in kinetic energy macroscopic plus change in potential energy macroscopic plus change in internal energy. This is what we have, okay? If the system is stationary, means if it's not moving, can anyone tell me what are these two quantities? Can anyone tell me what are these two quantities actually? What will be the value of those two quantities if system is not moving, if it's stationary? In a closed system, it don't have any outlet and inlets, it's closed, locked. Then what is this? Kinetic energy and potential energy macroscopics, 0. Okay, now you can understand, if for example if time is not there, this energy in minus energy out is equal to change in energy of the system, delta E of the system, which is same as delta U actually, okay? And this actually gives you energy in minus energy out is equal to delta U for stationary closed systems. For stationary closed systems. This is actually the first law of thermodynamics. Now, you have one very famous syntax or basically convention. Heat added to the system is positive. Mass conservation also, sir, please. I'll tell you. I'll deal open system, first law for open system, then I'll show you. Okay, just a minute. In this equation, you have this popular convention. Heat added to the system is positive. Heat taken out from the system is negative. Heat or work added to the system is negative. Work taken out from the system is positive. Actually, there is no need to remember all these things. This is the single equation which tells you all the things actually. Okay, you actually need not mug up. Heat added to the system is positive, and many times recently in my Telegram group also, you know, if some of you want to join my Telegram group, it is like t.me/pw. Vinay is my Sa is also there after that, so that's what my Telegram ID. So if you want, you can just go. If sub P is 0 because at same elevation, yes, delta P is 0. Okay, so delta P is 0 because of same elevation. It's not moving now, it is fixed. In this equation, if you have Q and if you have W, let's say, I'll ask you a question, guys. See here. You have gas. This is the boundary I am doing. I have a paddle wheel. Because of paddle rotation, because of the irreversibility friction here, friction generates heat, and let's say this is not insulated, for example, heat is going out, Q. Okay, you can understand clearly. Initially my paddle wheel is rotating, because of some external source I am making this paddle wheel rotate. If paddle wheel is rotating, then definitely because of the friction between the blade and the molecules, what happens? Heat gets generated. That's how actually entropy increases. So it is actually irreversible. Okay, now if you see, in this case, because of heat addition, let's say this is not insulated, heat actually goes out. Okay, and let's say these two are not same. Okay, for example, because of only some small leakage, heat is going out. Okay, let's say there is some insulation, but that insulation has some small leakage, so because of which some heat is going out. Then clearly, you know, if I want to write this equation, what you write? If I want to write first law for this, as per your syntax, Q minus W is equal to delta U, you will tell me Since heat is leaving the system, I should write minus Q minus, since work is coming into the system, I should write minus W is equal to delta U, and you will tell me to write minus Q plus W is equal to delta U. This is what you ask me to do. Yes or no? Are you all clear with this? Normally your syntax, I mean your convention, sign conventions. This is what you use to do the sign conventions. Correct? This is how you will make me to write this equation finally. Minus Q plus W is actually equal to delta U of the system. Okay? When writing this equation, the points you have to keep in mind is heat added to the system is positive, heat taken out from the system is negative. Since heat is going out of the system, you are putting a minus Q in that Q. Since work is coming into the system, in this W you are putting minus W, minus of minus is giving me plus. This is what you write. Normally, without doing this also you can write this. See, I'll just tell you. E in minus energy out should be equal to change in energy of the system. Since it is stationary, it's only equal to internal energy, change in internal energy. Now tell me one thing, out of this paddle wheel work and also Q, okay, let's say this is some energy, there is some energy transfer because of this paddle wheel, there is also some energy transfer because of this heat. Out of these two, which is coming into the system? Tell me. Out of those two, W and Q, which is coming into the system? Can't we account for entropy generation? Energy generation inside a system? No. Energy can never get generated, okay? That's what your conservation. In sun also energy is not getting generated, heat is getting generated, okay? Energy is changing from chemical form because of fission to heat, that's it. Okay, pay much? You can never generate energy, you can always convert from one form to another form, that's it. Even sun do not generate energy, it generates heat because of the nuclear fissions. Clear? So W is coming into the system. So the energy in which is coming is W minus. What is the energy which is going out of the system? Q. Q is going out of the system. So in case of energy out, write Q is equal to delta U. This equation and this equation are same. Minus Q plus W, W minus Q equal to delta U. Clear? So that's why if you use this equations in general, you need not generally keep in mind that heat added is positive, heat coming out is negative, and also some confusions come out whether this is work or heat. All these things, confusions are there, okay? Because last time also, few days back in my Telegram group, people are asking whether here energy transfer is work or heat, because I know what is the intention. By knowing it as work or heat, they want to substitute in the correct location out of these two places. Yes or no? If you don't have correct clarity that whether the transfer is heat or work, you will waste some time in deciding where to substitute the energy actually, okay? But if you use this simple equation, it's direct. You check all the energies which are coming, you put it at one place. You check all the energies which are going out, you put them at one place. The difference of those two is actually delta E of the system. Clear? Okay? Fine. So flow work, anyway, I'm just giving the idea. So if you have flow work also, then the system E of the system is like KE plus PE plus U plus PV is also there in case of open systems. For open systems, this is what you have. So in case of open systems, this guy is also there, and this combination is nothing but enthalpy, okay? So KE plus PE plus H is what you have. So if you want to write this energy conservation for open systems, so energy in, of course here flow rates will be there because movement is continuous of the system, is equal to change in energy rate of the system. And if an open system has all this stuff, then change in kinetic energy rate plus potential energy rate plus enthalpy rate. That's how you have the steady flow energy. I mean, this is actually the equation. If you make this delta E of S 0, then you can get the steady flow energy equation. That's it. Okay. So these are the things that you have in general. Energy in minus energy out is equal to change in energy of the system. And of course, here we are taking the rates. If time is not dependent, you can write this as small quantities. Q minus W is equal to delta KE plus delta PE plus delta H. All these things. Steady flow energy equation is what you can do actually. Okay. So anyway, you know these equations. Now my job is only to apply. Okay. So apply the thermodynamics. Correct. I'll assume everything is known to you. I'll just apply. Okay. Shall I do that? Shall I just apply or shall I do this also before teaching some things? Like for example, there are many nice interview questions actually in case of condensers. Today also, just before start the class, someone is asking me why vapor pressure of a effusion has to be very low. अगर नहीं है तो evaporator में cavitation हो जाएगा बस. Okay. Just mass conservation. That's it. M dot in minus m dot out is equal to d by dt of mass of the control volume. That's it. You put all inlets and all outlets. This I have already taught in this also, no? Like fluid mechanics also, mass conservations. You remember when we are talking about continuity equations, I was talking about this. And this is energy conservation. That's it. So this equation is always a time saver. Basically this is the first law of thermodynamics, this one. Okay. If you know this equation, then things are easy. Now let's get into the second law. So depending on different devices, you will see kinetic energy, potential energy are zeros, all these things. Like for example, if you want to apply this for nozzle, I'll just apply for nozzle and just leave it. For throttling and all, I will show you when I am teaching effusion. Okay. So for nozzle, you know Q minus W is equal to delta KE plus delta PE plus delta H is what you have. And in nozzle, clearly you know you won't get any work output, so you'll make this 0. Potential energies are also comparatively 0. You will make Q 0, correct? You have logics for these two because there is no shaft work which is getting generated in case of a nozzle, and also potential energy changes are very much small because clearly if there is a flight which is flowing, flight won't flow, flight actually cruises. So let's say if there is some flight which is moving at some height, say some 11,000 feet from ground level, sea level. If you have a nozzle here, turbine nozzle, between these two locations there could be some small potential elevation difference, but when you take the potential energy differences at these 2 points, will there be any significant potential energy change between the fluid? Will there be any significant potential energy change of the fluid between these two places? Come on, quick. No, correct? There won't be much potential energy changes that generally happen. So clearly you can understand that I'm erasing this. This potential energy is also 0. Can anyone tell me why I'm making this term 0? Because it should have some logic, correct? This, there is no shaft, nothing, so it don't generate any work like turbine and all, so we have neglected W. We have neglected PE because there is certain logic. Why Q is neglected? Because we don't like Q, correct? Is that the answer? Since we don't like Q, so just take it out. Because gas expands very fast. Alright? money Sachin, I know if the process is, if the flow is adiabatic, then definitely no heat interactions. But you know one thing, I'll ask you one thing. Heat requires some time. Yes, exactly. Okay. So see here, I'll tell you one point. No heat generated in nozzle. This is not generation, this is the net transfer across the control surface. Okay. I'll tell you one thing. Even if it takes long nozzles, which is like 10 meters length and all, either the heat to go out or the heat to come inside, Q dot into time is what we have. In case of nozzles, generally what happens in case of subsonic fluid accelerator, and in case of supersonic, we will see what is subsonic, supersonic and all. The gas molecules here, it will cross this 10 seconds, maximum in some less than 1 second. Okay, so 0.02 seconds or something. Whenever this time is very much 0, then clearly the net effective heat interaction that happens will also tend to 0. Like many of you might be playing in kitchen, you will just touch the hot objects and remove your fingers from there. Okay, just touch it and remove. Don't keep it for some long time because you will get hurt. So just touch it and take your fingers out. You won't get hurt, correct? Because for the burning of this finger, some amount of heat has to be transferred from hot object to your finger. Okay, but even though there is heat transfer rate, you are not giving sufficient time for sufficient amount of heat to touch your finger. Got it? Same thing happening here. Okay, so that's why this Q is 0. Clear? Because by the time this hot gas molecule travels from here to here, it don't find enough time to exchange heat with its surroundings. Clear? It's not quasi-static, yes, it's highly, irreversible flow in actual case. Normally for mathematical easiness, we take reversible flows, but actually like how we have turbulent, similarly irreversible flows are very difficult to analyze. Clear? So anyway, this is how we make the things zeros actually. So we'll generally write. So this implies V square by 2 plus delta H or dH is equal to 0, or if you write V dV plus dH is equal to 0 for nozzles. Okay, and then you substitute your ideal gas, all these assumptions. Delta H is Cp times T2 minus T1. This V dV, again velocities, you can do integrate from V1 to V2, all these things you can get relation between velocities and temperatures. Okay, normally in case of nozzles, normally in case of subsonic flows, I'm telling, inlet velocity is actually very less as compared to the outlet velocity. So generally when you have V2 square minus V1 square, we eliminate V1 square generally. Okay, so that's how we'll, if you see, many of you might have seen this equation, V2 square minus V1 square is 2, fine. V2 is equal to square root of 2 Cp T2 minus T1. You might have seen this equation, many of you. Okay, velocity at the outlet of the nozzle, but one important thing is this Cp should be substituted in joule per kg Kelvin, not in kilojoules. Okay, because this is in meters per second. Clear? Root 2ghr, no. Okay, so this equation you might have seen, because this is basically from this equation. If you integrate this, V dV is equal to minus dH, H1, H2, V1, V2, and you can also write this sometimes as T1, T2. If you make a perfect gas assumption, this becomes Cp dt. If you do this, and if you put this V1 tending to 0, you will end up with this. Okay, so is this clear to all of you? Basically from this equation, this integration gives you this. Okay, now let's get into some basics of entropy before we wind up the sessions, because majorly when we are analyzing cycles, thermodynamic cycles, TS diagrams are of much importance. Okay, so again, I'm not deriving all the 𝐂𝐤𝐴 inequality and all, I'm just utilizing it to show you a few things. Okay, we know certain things like we have Kelvin and also 𝐂𝐤𝐴 statements. This generally gives the idea of heat engines, because you know, I'm not again writing the statements and all, because all of them are done in your basic thermodynamics course. So how adiabatic process is work? Sorry, didn't get you. Ankit, आप हिंदी में पूछिए, कोई दिक्कत नहीं. How adiabatic processes work on heat transfer? Normally जो process adiabatic होता है ना, so वो process generally work consuming होता है, and also in expansions, internal energy of the system is utilized to generate work. Okay, so मान लो कि आपके पास Q minus W is equal to delta U है, Q is 0. So what happens? Work generated is at the decrease of this internal energy. Clear? अगर एक adiabatic system काम किया तो उस system का pressure या temperature दोनों में एक चीज, or maybe both the things, or velocity something may get decreased definitely. Like in this case of nozzles. In this case of nozzles, what happened? Kinetic energy of the fluid increases at the expense of enthalpy. Okay, so जब flow होते हैं इस nozzle में H1 to H2, in case of subsonic, okay, normally velocities are low and all. In this case, Mach number is less than 1. In this case, when velocity is increasing, definitely V1 is greater than, V1 is less than V2, but H1 is actually greater than H2. Enthalpy drops. Clear? In such cases, that's how we actually generate the effects. Okay. Now, anyway, let's see. So, heat engines, and this gives you the concept of refrigerators. You might have done all those diagrams, like where you have a cyclic device, then source, sink, all these things you might have done. Okay. Now, main important point I want to discuss is, we have something called, from second law, we get one thing which is called 𝐂𝐤𝐴's inequality. 𝐂𝐤𝐴's inequality. What does this 𝐂𝐤𝐴's inequality tells you? If there is a device, cyclic device, and if this is the control surface, because device will have some volume, so this is the control surface. So let's say different points on this body are at different temperatures, T1, T2, T3, and so on, like this you have. Similarly, I'm not deriving this as of now because time is short in fast track. So let's see, some amount of heat is flowing here, del Q1, del Q2, maybe something here flowing is out, del Q4, maybe something flowing here is del Q7, something like this, and something going in, del Q8, something. This 𝐂𝐤𝐴's inequality tells you the cyclic integral or the complete boundary of del Q by T across the complete boundary. Means if you take the small amount of heat interaction here and also divide it with T, okay, plus again the small amount of interaction here with sign, okay, going in is positive and coming out is negative because of this is actually derived from energy first law of thermodynamics. So that's why this is less than or equal to 0. So this equality is for reversible cycles and this less than is for irreversible cycles. You can show this actually, but it takes certain time. Again, we have to connect a cyclic device to a piston cylinder assembly, all these things. Then apply first law of thermodynamics separately for cyclic device, separately for first law, separately for this piston cylinder assembly. Then add both, simplify mathematically, all this stuff. After you do a lot of things, we will actually get this cyclic integral del Q by T less than or equal to 0. You might have seen this in basic thermodynamics. Now, one thing I want to pick from this is the two things actually comes out from this equation, from this inequality. One thing is this actually gives you entropy is a point function. And it also gives you entropy generation is path function. Is path function. These two things you can actually, these two are consequences of this Clausius inequality. If you take a system, for example, if you take this system from state 1 to state 2, it doesn't matter whatever the process you take, the entropy change between these two states will always be same, specific entropy, okay. And also if you take the system, like I'll just give you some small understanding here. If you have a process, for example, take two coordinates x, y, maybe pressure, volume, whatever you want. If there is some small process which is happening from this location to this location, ds is actually given by integral del Q by T in that process plus delta S generation, specific, okay. Let's put specific terms. This is what we have, okay. And this ds will be same even, this is a small process, even if the process is this, or even if the process is like this, okay. So even if the process is like that also it is same, because you can ask me if these three processes are different, how this can be changed, because these two gets adjusted in such a way this value always is constant, clear. And you know heat is a path function which you can understand from the first law of thermodynamics. This del Q by T will not be same in all these three processes, it will be different, and accordingly you will have this delta S generation, clear. So I can't see, enlarge please, okay, sorry. Then I'll write one thing, delta S is equal to integral del Q by T plus entropy generation in the process. If you have two properties, for example, pressure, volume, or pressure, temperature, whatever, if you plot a process between two states, this is state 1 and this is state 2, this delta S between 1 to 2 is always same with any process what you take. It depends on entropy generation. Yes, of course, it depends on entropy generation. If process is reversible, this entropy generation is 0, which you can again show from this equation, Clausius inequality. For reversible cycle, if you take this equal to 0, and then by splitting up the cycle into different parts, you can actually show this entropy generation is actually 0 for reversible cycles, okay. And if process is irreversible, this entropy generation is not negative, and clearly it is generation term, so this will be always greater than or equal to 0, clear. So entropy generation term will be always greater than or equal to 0. Now for a process, we talk about isentropic process a lot, okay. So before I go for isentropic process, I just want to give you one thing about this work interactions here. Look, normally if you have PV power n equal to constant, I'm explaining for polytropic so that by changing values of n you can get for anything, okay. So PV power n equal to constant. If you plot this on a PV diagram, for example, okay, so let's see. If you plot this on a PV diagram, if you put n equal to 0, ideal gas, okay, I'm talking only about ideal gas as of now, no real gases. ideal gas. Okay, n equal to 0 implies if you put n equal to 0, v power 0, anything to the power 0 is 1. So P into 1 equal to constant. For n equal to 0, this process is nothing but constant pressure process. Correct? So therefore you can see constant pressure process is something like this, 1 to 2. Then after, for n equal to 1, you have PV is equal to constant, which is isothermal. So clearly, xy is equal to constant, rectangular hyperbola, you will get some line like this. And if I am doing it for the same volume, okay, n equal to gamma, this gives you PV power gamma is equal to constant, which is adiabatic. Clearly for adiabatic ideal gas, it comes down something like this. You can ask me, who told you that it will come down? Okay, this is n equal to 0, n equal to 1, n equal to gamma actually here. Okay, some of you can ask me, how do you know if this is isothermal and this is adiabatic? How do you know adiabatic lies below isothermal? The one thing I can do is mathematically, if you have PV power n equal to constant, if you differentiate this, P into n into v power n minus 1 dV plus v power n into dP is equal to 0. Correct? So you can see, if you cancel this v power n all over, you can get a v here. So dP by dV is equal to minus n times P by V is what you have here. So one thing I want to tell you, as this n increases, dP by dV increases. Okay, means slope of the line increases. Clear? Sorry, Sgen is equal to 0 and del Q by T equal to 0 for reversible process. For reversible process, del Q by T is not 0. Okay, only for adiabatic it is 0. I'll tell you. So physically it's telling whenever any thermodynamic process executes and do not left any effect in surroundings, and hence entropy changes 0. Look, I'll go back to the entropy equation just a minute. Okay, first of all I want to tell you a few things, then connect it to entropy again. Okay, so see here, this is what you have. First just look here, I'll go back to the entropy equation to make you understand the things. If you see, as n increases, dP by dV increases. Okay, so when dP by dV increases, then clearly what happens here, let's say if this is V1, my system is going to V2 to the same volume via different process. If dV is same, as n is increasing, for the same amount of dV in any process, as n increases, can I say dP increases, means change in pressure has to be large for larger value of n. Can I say this? For reversible, entropy generation is there. Entropy generation is there, not entropy change. Okay, entropy change can be there. I'll show you just a minute. So please see here, dP by dV is this what you have. Can I say as n is increasing, for same change in volume in any process, dP has to be large if n is large. Correct? So if you compare isothermal and adiabatic, n is definitely more in adiabatic, because clearly gamma is equal to, you might have seen this in basic thermodynamics, 2 by F. F is the degrees of freedom, and for monoatomic gas, F equal to 3. So gamma is 1.67, 2 by 3, 1 plus 2 by 3, 1.67. For diatomic, like hydrogen, nitrogen, oxygen, air, all these things, n equal to 5, F equal to 5 actually. So that gives you 1 plus 0.4, 1.4, and triatomic, F equal to 6. Okay, so degrees of freedom of molecules, so 1.33 for triatomic, like CO2, NO2, SO2, all these things. Okay, so anyway, so pressure has to increase. So if you compare, the pressure drop in isothermal has to be less as compared to pressure drop in adiabatic. Okay, so that's how I know adiabatic is actually below isothermal. Clear? So that's how, if you go in this clockwise direction, n increases actually. Now one thing I want to tell you, normally in case of tomorrow when we are start doing A standard cycles, okay, when we are talking about A standard cycles, in case of A standard cycles we assume closed system. Okay, normally cycles are open, okay, because air fuel mixture goes in, all these things happen, but for thermodynamic analysis we make them closed cycles. In closed systems, clearly in case of expansions and compressions, in case of expansions you can say this cannot be done. Okay, why? If this is your case, pressure is actually constant, but when things are expanding, pressure changes in the diagram. Okay, because let's say some high combustion happened, there is a big blast and there is some pressure. This pressure is actually responsible for the pushing of the piston. Okay, so when this pressure is pushing the piston, when piston is moving, after combustion got finished, pressure actually decreases. Okay, so that's why this constant pressure process is generally not taken in Otto cycle, okay, for combustion. Okay, out of these two, normally you see in majority of the cycles we take isothermal compressions and expansions. Even in open system, for open systems we'll see work interaction, we project the area onto here, onto pressure axis and all, we'll see that. In this n equal to gamma, out of these two, area under PV gives you work. So this is the work in isothermal and this is the work in adiabatic. Clearly in adiabatic expansion you will get less work. Okay, even if you are expanding to the same pressure, you can see if this is PV, let's say this is your pressure and this is the pressure range of operation. From this system, if you expand it along isothermal or adiabatic, then clearly you can see this area in case of adiabatic will be less as compared to isothermal, because in isothermal this would have been the total area. But practically conducting in isothermal process is very difficult. You might have seen normally for simple device, your cycle pump, when you are fitting your cycle pump to your tube, to your cycle wheel, and if you start pumping air, immediately after some time you will feel there is some hotness touching your leg. Yes or no? Means if the pump gets touched to your leg, you will feel hotness. The air inside gets heated up. Can you see? Compressions will always generate heat. Clear? So that's why even though practically, even if you reverse the cycle, PV between two pressures like this, you can see, maybe if I am doing this as this case, n increases clockwise. So if this is isothermal and this is adiabatic, in case of open flow devices, for example, you say pumps, all these or maybe turbines everywhere, even though this is isothermal, is requiring less work for compression, and also adiabatic is giving higher work for compression. In these two cases also, practically this isothermal is very difficult to achieve. Okay, so that's why we make all the compressions to be adiabatic. Okay, now when it comes to reversible adiabatic, now you go back to this equation. In this equation, guys, I'm telling you, if process is reversible, only this term is 0, not the complete delta S, because this can still be there. Okay, if I am doing reversible heat addition, for example, okay, reversible heat addition, if I am doing reversible heat addition, you can see ds is equal to del Q by T plus delta S gen, small generation. Okay, then you can clearly see this is 0 because of this reversible makes this 0. Now heat addition, this tells me that this del Q is actually positive. This is positive, this is positive, so ds is actually positive. Clear? That's why in your constant volume process anywhere, if you are plotting Ts, you will always do in such a way, if heat is added, entropy should increase clearly. This is how you draw the curve. Temperature and entropy both increases. Clear? Chinnappudu experience chesa, good. Okay, so see this is because in case of ideal gases, normally in case of where gamma, in case of adiabatic expansions where gamma is equal to n and all, normally in case of any expansions except 1 less than n less than gamma, there is some special case which we will see. But normally when you are adding heat to a finite amount of mass, what happens is temperature increases. Along with the temperature, ds is positive. That means along the process, entropy should increase. The line which gives you both temperature and entropy increase will be like this. That's why in your Otto cycle and all, you might have seen in case of constant volume heat additions, curve goes like this. सर एडियाबैटिक एंड आइसोथर्मल इन क्लोज्ड एंड ओपन वाला समझ नहीं आया सर. देखिए मोहित, मैं दूसरा बार एक्सप्लेन करता हूँ. In case of closed system, for example, or for example, if you say, yeah, it's closed, generally piston is moving. In that case, normally, you know, displacement work, integral PdV. Okay, of course, you put this also small. Then area under the curve projected onto volume axis in case of closed systems, and in case of open systems, look here. I'll just tell you one thing. Here, yeah. For open systems, you can understand one thing. Heat transfer into the control volume minus work interaction of the control volume is equal to change in kinetic energy plus potential energy plus change in enthalpy. Okay, so this is what you have. Now clearly if it's an isentropic process, normally this is 0, these two if you neglect in case of isentropic devices like turbine, pump, all these things are isentropic. Turbines and all, definitely they have to be isentropic, otherwise heat loss will happen. Okay, so that's why we put very strong insulation across turbines. So that's why Q is 0. These two if you neglect, because compared to enthalpy these values will be very small. You can understand WCV is equal to minus DH. This is what you have. Okay, from this equation WCV is equal to minus DH. You all know TDS equation. TDS is equal to, normally from energy equations you can write this, minus VDP. Now clearly you know it's reversible. Every device we assume it to be reversible actually, and if Q is 0, I can make this reversible adiabatic as isentropic, because in this equation making reversible assumption makes this 0, making adiabatic assumption makes this del Q 0. 0 plus 0, this is 0. That's why reversible adiabatics are isentropics actually. Okay, so see here this value, so DH is actually equal to minus VDP. Okay, so WCV is equal to minus VDP. This is plus actually. Okay, DH is equal to VDP, because if this is 0, that means DH is equal to VDP. Na? This is VDP. So if you substitute here, this is the case, and this is del W, because these are elemental things, because we have taken differentials. So del W. So if you want to integrate, work interaction in a control volume is equal to minus integral VDP. That's what you have here. Okay, and this equation is very helpful when you're calculating pump work in a Rankine cycle. Okay, we'll see all these things, and minus VDP. So anyway, now coming to this case, if process is reversible, only this part is 0, not this. You can have heat addition or heat rejection depending on this. Now one important point I want to tell you, which before we move for the next things. Okay, tomorrow when I start A standard cycles, I'll teach you more things. One thing that I should teach here is reversible adiabatic. If you take this reversible adiabatic process, this is actually called isentropic. The reason for this is actually, if you have small change in property, this is del Q by T plus delta S generation. Okay, delta S generation. Now clearly because of this reversible thing, this is 0. And because of adiabatic thing, this is 0. So we have ds is equal to 0, which means s is equal to constant. So reversible adiabatic processes are called isentropics because you have certain lock for the entropy. Entropy cannot change actually. So take the pump example and explain it using graph under the adiabatic compression process. I'll do it when I'm teaching a Rankine cycle, when I'm calculating the pump work. Okay, because I think I am already 4 minutes over time. But yeah, okay, so when I'm taking a Rankine cycle, when I'm talking about the pump work, I'll definitely use that expression WCV is equal to minus integral VDP, and I'll show you how pump work can be calculated and why adiabatic is coming. Tomorrow I'm going to start A standard cycles, basically auto, diesel and also dual cycles, but don't miss the class. Don't feel that you know the things, because I'm going to explain you why constant volume heat addition in case of auto, why constant pressure heat addition in diesel, okay, and why dual cycle is in that particular shape. All these things. Fine. Last line, okay, before today's class. The reason for this is, see here, because of heat rejection, this term can be negative, and because of irreversibility, this is always positive. If magnitude of del Q by T is same as magnitude of delta S gen, then clearly this is 0, but the process is not adiabatic. Okay, so because of that, it's okay, Preet, you can just watch the video for tomorrow. Okay, tomorrow again at 4 PM we'll start the session. Okay, so anyway, when in tomorrow's class, when I'm talking about constant volume, constant entropy, constant entropy, of course, isentropic process, all these things, I'll show you how graphs are getting generated, and also in case of diesel cycle, how constant volume and constant pressure has different slopes actually. Okay, so we'll see all these things. Clear? I think a lot of refreshment happened today, at least in the case of entropy and all. So we'll use these things. So how many lectures? Total 12 lectures, 12 to 13, I guess. Yeah. Okay. So anyway, properties of pure substances, something related to this. I'll directly talk. I thought of solving 2 questions also, but okay, time. I'll leave these 2 questions as homework. So please, try these questions based on your thermodynamics knowledge. If you cannot solve, I'll solve for you tomorrow. Okay. But please try before coming for class 1 and also 2. Yeah, this is, I think, properties of pure substances. But anyway, open system devices, and this is unsteady first law. Okay, unsteady control volume analysis, unsteady flow equation. Yeah, tomorrow basically I'll start IC engines. Okay, I'll talk about cycles. These lectures won't be in Hindi. From tomorrow I'll try to definitely use Hindi as much as I can. Okay, क्योंकि मेरा हिंदी इतना अच्छा नहीं है, so इसलिए मैंने हिंदी में नहीं पढ़ा हूँ. लेकिन कल से मैं कोशिश करता हूँ कि मेजॉरिटी ऑफ द क्लास मैं हिंदी में लेता हूँ. ठीक है. Fine. So 2-minute summary. We have reviewed basic thermo. That's it. So when I'm drawing curves and all, tomorrow I'll explain you how we have to convert the graphs and all. Okay. How to plot PV. Then from PV, how to convert to TS. Then using first law, second law. All these things. ऐसा कुंजम हिंदी is fine. Okay, fine. सर हमारा इंग्लिश उतना अच्छा नहीं है. लेकिन भाई मैं आपको एक चीज़ ठीक है, fine. This is what you have. Okay, so we'll close the session first, then we'll have some small fun and we'll leave. This is my Telegram ID. If you wish or if you feel that I can help you somewhere, you can definitely join that. There are some of your friends, already 600 plus friends of you. They'll also discuss about things. Saka math is illuded. What is your favorite subject? Heat transfer. Heat transfer is my favorite. Okay. And इंग्लिश के बारे में मैं एक्चुअली एक चीज़ बोलना चाहता हूँ. ओके, आफ्टर दैट विल क्लोज द सेशन. एक्चुअली अगर आपको एक PSU में काम मिला या लेकिन मान लो कि आपने फॉरेन यूनिवर्सिटीज़ में पढ़ना चाहिए, तो डेफिनेटली इंग्लिश एक बहुत एक्सलेंट ऑप्शन हो जाएगा. ओके, एंड ऑल्सो इफ़ यू गेट एडमिशन इन IITs और IISc, जनरली आपको किसी भी प्रोफेसर हिंदी में नहीं पढ़ाते हैं उस टाइम पे. ठीक है. And you will be in such a situation, you cannot ask them, sir समझ में नहीं आया और एक बार बता दीजिए in Hindi. Okay, you can ask them, I didn't understand, you please explain, but you cannot tell them that please explain in Hindi again. Okay, so that's what you cannot ask generally. So better, yeah, ठीक है, बेसिक चीज़ अंडरस्टैंड होने के लिए हिंदी ठीक है, लेकिन अगर आपको थोड़ा सा एक्सलेंट कॉलेजेस में पढ़ना चाहता है लेकिन PSU का इंटरव्यू स्टार्ट करना पड़ेगा. गेट का पेपर हिंदी में नहीं आते पक्का. यू ऑल नो, आई होप यू ऑल नो दिस. सर बिट तेज है इंग्लिश सर. स्पीड आई मीन, या आई ट्राई टू रिड्यूस माई स्पीड. ओके, क्योंकि हम ये बुलेट ट्रेन का मीनिंग मतलब वी हैव टू जस्टिफाई द बुलेट ट्रेन ना, दैट्स वाई. ठीक है, फाइन. एनी हाउ पता है, लेकिन मैं कल से थोड़ा सा आराम से पढ़ाता हूँ. ठीक है, इतना तेज से नहीं पढ़ाता हूँ. हाउ टू प्रिपेयर फॉर BS एक सेशन है. ठीक है, मैं कल सेशन पे एक्सप्लेन करता हूँ क्योंकि वो थोड़ा सा एलोबरेटेड प्रोसेस है. सर हीट एक्सचेंजर का PDF मिल जाएगा. मैंने कहीं जगह पे हीट ट्रांसफर ऑनलाइन नहीं पढ़ाया, एक्चुअली ऑफलाइन ही पढ़ाया था अभी तक. FM में ये बोला था सर आपने. ठीक है, आई विल स्लो डाउन डेफिनेटली. सर हाउ टू प्रिपेयर फॉर इंटरव्यूज, सब चीज़ मैं इस कोर्स के एंडिंग तक पढ़ाता हूँ. ठीक है. सर आपका हीट ट्रांसफर का लेक्चर मिलेगा. नहीं, ऑनलाइन में नहीं पढ़ाया अभी तक. ठीक है. ओके, फाइन. सो विल मीट टुमारो अगेन एट 4 PM. विल ट्राई टू लुक एट IC engines. I'll teach you A standard cycles and also bit of testing of IC, like indicated powers, break mean effective powers, all these things. We'll look at some basic stuff. Okay, fine. Then take care. We'll see you all at 4 PM tomorrow. Please don't miss the sessions. Okay, have some continuity. Okay, fine then. So any doubts? I think no, everything is fine. Okay then. Thank you all. Thank you. Take care.